Good afternoon, everyone. Welcome to the last season of the BRAG this year. We had a great season, and closing the season as the last episode of the season, we have the pleasure to have Renato Vidal Martins from UFMG talking about the gonality of an integral curve. Renato, please go ahead.
So, Marcus, thank you for the invitation. This is a joint work with Steve, the gonality of an integral curve. So, here is an outline for the talk. I'm going to start with some backgrounds, results on gonality for smooth curves and Gorenstein curves. Then I'll address the integral curves, the integral case, linear series via torsion-free sheaves, and a recap, a review on scrolls and canonical models. Then I'll state some results on low gonality and gonality via scrolls and canonical models. And at the end, I'm going to discuss a bit an upper bound on gonality, results for smooth curves, the integral case also. So here is our setup. C is an integral and projective curve. G is the arithmetic genus of C. O is the structure sheaf. Omega is the dualizing sheaf. C bar is the normalization, and nu the normalization map. So now I'm going to state some distinctions among curves. So C is smooth if C equals C bar. C is hyperelliptic if there is a morphism C to P1 of degree 2. C is Gorenstein if omega is invertible. It can be possibly singular and or hyperelliptic. C is a canonical curve if C is in Pg-1 and omega is OC1. So here there's this result by Rosenlicht. Assume C is Gorenstein, then omega defines a morphism K, C to Pg-1, and if C is non-hyperelliptic, then K is an embedding and Kc a canonical curve. If C is hyperelliptic, then K is a double covering of the rational normal curve. So Rosenlicht didn't use the term Gorenstein. The term Gorenstein was not used in print until 1960, more precisely November 21, in a seminar by Serri. And here are other proofs of the same result made by these authors. And finally, if C is non-Gorenstein, then it is necessarily singular and non-hyperelliptic. So let's address now the gonality in the smooth case. So the gonality is the smallest d, such that there is a morphism C to P1 of degree d. And the gonality of C is 1 if C is P1. The gonality of C is 2. If gonality of C is 2, then C is hyperelliptic. 3 if it's trigonal. 4 tetragonal. 5 pentagonal, and etc., etc. Now I'm going to state a very famous result by Henriques and Babbage. Let C be in Pg-1 be a smooth canonical curve, then either. You likely know that. C is cut out by quadrics. G equals C, 6, and C lies on the Veronese surface. So C is isomorphic to a plane quinic. And C is trigonal. C lies on a twofold scroll whose rulings yield a triple cover. Okay. So now I'm gonna address the gonality in the Gorenstein case. So there's this result by Carlotto and Renata in 2001. If C is a Gorenstein canonical curve on a cone, then C meets the vertex in a singular point and the ruling meets C 3 times. So there's this picture, which is a comparison between Henriquez Babaj and Ster. In Henriquez Babaj, we have a morphism, a triple cover, and we have a triple cover of P1, and there is a morphism. In the case of a cone, the curve passes through the vertex, and there's only a G31. But one can gather those pictures in a unique result, and this is what they did. They proved that C is trigonal if and only if C lies on a two-dimensional scroll. But here, trigonal, the term trigonal is something that we're going to state right away. I mean, what does mean trigonal in this sense? Okay. So now I'm going to address the gonality in the arbitrary case. So we have to consider 3 problems, or it involves 3 parts: replacing morphisms by pencils in the definition of gonality, and bundles by torsion-free sheaves in the definition of pencils, finding a canonical model if C is non-Gorenstein. The problem is that if C is non-Gorenstein, we don't have a K from C to C prime. And considering singular scrolls and of arbitrary dimension. So let's take care of part 1. I will show an example. I think it's gonna illustrate how it works. So take this curve, T3, T4, T5 in P3. It is contained in a cone. Here is the picture of the curve. Let's take some points here, P and Q here. And note that the blue line meets C at 2 points, PT and P. And there's a special line here, LQ, which meets C at 2 points, P and Q. P and Q. And geometrically, this is a pencil of degree 2 with a non-removable base point, a notion introduced by Ster and Rosa. And why is it? This point is a non-removable base point of the G21, because if you remove this point, we're going to have a G11. And if we have a G11, we are going to have that C is P1, but it's not. So now I'm going to formalize these things. So a linear series on C of degree D and dimension R in the smooth case is, well, you know, it's a pair of a divisor OD, V, where D is a divisor, the degree of D is D, V is a subset of the global sections, and the dimension of V is R+1. In the general case, we're going to note Altman and Kleiman 1976 approach, where a linear series is a set of exact sequences, where is a pair of FV. F is a torsion-free sheaf of rank 1, V is a subspace of the global sections. I in this sequence is home F omega, lambda is a global section, and I lambda is home lambda omega. There are some technical reasons for this, but I won't comment here. I will just say how this works in our example. In our example, I mean, we have a G21 there, and then the sheaf F is O1T. The sheaf F O1T is the one which computes the gonality, and it's isomorphic to omega, the dualizing sheaf, but it's a special case. V here is this set K union with AT minus B, where K here, well, for sure, the space of global sections is this, generated by 1 and T, so okay. But I put a union of K and AT minus B because K has to do with the yellow line there, the yellow line here. And this part has to do with the other lines, believe me. So L is called a GDR, a pencil if R equals 1, and the system is complete if the global sections are, the V is all global, all the global sections. Now let's formalize the notion of a base point. P is a base point of the linear series. Well, if lambda P from OP to FP is not an isomorphism for all lambda. And P is an unremovable base point if it is a base point, and it's also a base point of a reduced linear series when you take only the sheaf generated by the global sections. And the gonality is the smallest D, such that C has a GD1. So part 2, the canonical model. So let's talk about the canonical model. Let nu from C bar to C be the normalization. Consider this linear series where F is the pullback of the omega moded out by torsion. And you take the global sections of the dualizing sheaf and you induce a morphism from C bar, the normalization, to PG minus 1. And then you're gonna define that set that C prime, the image of this morphism, is the canonical model of C. So this is what plays the role of a canonical model, especially for an Ungorenstein curve. And then there's this result by Rosenlicht, 1952. It's a crucial result. The normalization map C bar to C factors through C prime. All right. So part 3, don't know if you still remember, we are in part 3 addressing scrolls in singular case. Well, it's just to recap this. There are at least 3 ways of seeing an S-dimensional scroll, and you likely know that. One is the set of points such that the rank of the matrix below is 1. Another one is the image of a projective bundle, OP1, where MI, M1, M2 are the parameters of the scroll. And the third way is that S is the union of S minus 1 planes determined by parametrist points on S rational normal curves of degree mi in complementary spaces on Pn. Okay. So now we're gonna talk about our work with Steve. And the interesting thing is that here nothing's for free. Even for gonality 1, we should consider it's not that immediate that the gonality of 1 implies that the curve is P1. We start by a result that if a linear series computes gonality, then it is complete. Here is the proof. Well, I'll skip this part. The second result we need is a version of Clifford inequality for singular curves. If H0 and H1 are greater than 1, then the sum not exceed G plus 1. And the proof comes from an argument by Kempf in 1971 that if we have an undegenerated map A times B to C, then we have this inequality, dimension of A plus dimension of B is smaller than dimension of C plus 1. And this natural multiplication map, you just apply this result to this and you get the result. And now we are able to prove that gonality of C is 1 if and only if C is P1. Suppose degree of F is 1 and H0 of F is 2. Note that here we are already using the first result. Then H1 of F is G. And if G happens to be greater than 1, then you can apply Clifford. Then H0 of F plus H1 of F is 2 plus G, which is smaller than G plus 1. And this is a contradiction. So G is 0 and C is P1. Now let's address gonality 2, base point 3. I start by a result by Rosenlist, 1952, if C is hyperelliptic. Then it is Gorenstein. Then this result by Steer, Carlotto, from 1999. If C is hyperelliptic if and only if C is isomorphic to a curve of degree 2G plus 2 in PG plus 2 on a cone S, not passing through the vertex. S here is written as a scroll. And then I'm going to state a result, which is our result for gonality 2 base point 3. Assume G is greater or equal to 2, then the following are equivalent. C is hyperelliptic. C is isomorphic to a curve of degree 2n plus 1 in Pn plus 1 on a cone S meeting the vertex at a simple point. And so A and B is sort of a version of the prior result, but then go a bit farther. C prime is the rational normal curve of degree D minus 1 in PG minus 1, and K bar C bar to C prime is a double cover. C is Gorenstein and carries a G21. The gonality of C is 2, computed by a base point 3 pencil. And if B holds, then N equals G, and K C to C prime is the projection from a ruling. Now I'm gonna highlight some words here. Here we go. Hyperelliptic, simple, double cover, Gorenstein, base point free. Why so? Because this result gonna have a sibling, an equivalent for Gonality 2 base point. So before that, let's define C nearly normal if it has just one singular point, where MP is the conductor, the maximal ideal is the conductor. And then we're going to have this result. Assume G is greater or equal to 2, then the following are equivalent. So I would like to compare both results. So first, C is rational nearly normal, which is, I mean, the other side, the non-Gorenstein side of hyperelliptic. Then pretty much the same sentence. C is isomorphic to a curve of degree 2n plus 1 in Pn plus 1 on a cone S, but meeting the vertex at a singular point, C. C prime is the rational normal curve of degree G minus 1, and K C bar to C prime is an isomorphism. C is non-Gorenstein and carries a G to 1, so Gorenstein, non-Gorenstein. And the gonality of 2, gonality of C is 2 computed by a base point by a pencil with a non-removable base point. Here we also have an additional statement. If B holds, then N equals G. So we can gather this to have a corollary, which is interesting in some sense. C is 2-gonal if and only if C prime lies on a one-dimensional scroll. So we have that, I mean, the same result for trigonal curves holds also for gonality 2. That C is 2-gonal if and only if what we have here. C is 2-gonal if and only if C prime is a rational normal curve. But a rational normal curve is a one-dimensional scroll. Okay. So now we're going to address the general question. Is it true that C is D-gonal if and only if C lies on a D minus one dimensional scroll? The answer in the smooth case, at least necessity. Necessity comes from this, a result by Andreotti Meyer, Schreier, and Eisenbud Harris. I picked up this statement from Eisenbud Harris, their paper. Let X not a curve, any projective variety which is linearly normal, hyperplanes cut out a complete linear series. Then, if D moves in a pencil, then the union of the linear spans of the pencil is a scroll. And the proof, it's not a proof, it's a reason. You take the sections defined by the linear series and consider this natural multiplication map. V H0OX age minus D to H0OX age. And S is the variety of the ideal of two minors and is a scroll with this dimension. So if you wanted the result for the curves, just take X, a curve, age, the canonical bundle, the degree of D, and then you do the count and apply him and Haw, and you're going to have that this dimension is D minus 1. So we have sufficiency, necessity, we have this arrow to there. If C is diagonal, then C lies on a D minus 1 dimensional scroll. But in order to have the other way, one should consider minimality of dimension of S. And well, at least I've never seen in the literature, there might be, I don't know, but for smooth curves. So now let's address the problem of scrolls for singular curves. There are many issues. I'm gonna list some problems to address. First, C doesn't work at all. If you put here C, I mean, C is diagonal if and only if C, no way. So we should consider C prime instead. We're gonna see how. Second problem, sure. C prime may pass through the singular set of S. I mean, this happened in the trigonal case, in the two-gonal case, and actually C there, but we're gonna see that C prime as well. Then, in the smooth case, we have only one curve, C. Here we have 5 curves to consider. The curve C bar, the normalization C prime, the canonical blow up, because this part, I mean, this problem has its intrinsic part, and at the end also the canonical lift, which is you take C prime on a scroll and then you take the lift in the projective bundle. Okay. Other problem, C prime may not be linearly normal, a result by Steve and I. C prime is linearly normal if and only if C is Gorenstein or had just one non-Gorenstein point, which is almost Gorenstein. The problem here is not, well, what is almost Gorenstein? But I'm just stating this, that because, I mean, to see that this thing is rare. So, and at the end, this is the main problem which I've never seen addressed. Like, if C prime lies in S by L, does the series cut out by the rulings of S recover L, and how? So these are the questions which we answer by means of a lemma and a theorem. Lemma. Given any pencil on C, any pencil on C, FV on C induces an inclusion C prime on S, where S is a scroll with dimension S, degree of F minus 1, H0 of F minus 2. So here, just pay attention that we are taking, oh, sorry, whoops, what did I do? Oh. Just pay attention that we're taking a linear series on C to induce an inclusion on the scroll. And then we have a converse that if C prime lies on a scroll, then there exists a pencil on C with F generated by V, which induces an inclusion C prime on S with C prime on S and S on S prime. And then we refine this. I think this is a crucial part, that we can take C prime lies on a scroll S with smaller dimension, such that the inclusion is induced by a complete pencil on C. Here is the, I mean, I think that this was the key. effect. And then a characterization of what is the lift? Suppose C lies on a scroll induced by FV. Sorry, it's C prime. Then the canonical lift C2 prime is the blow up of C along omega and F. This is interesting, I think. So at the end, we get this theorem that the gonality of C is D if and only if C prime lies on a D-1 fold scroll and cannot lie on a scroll of smaller dimension. So here is the proof for A. It's just a reason. So let's, well, I just wanna mention how the scroll appears. So recall that FV, the linear series, is a set of exact sequence. Take P, the projectivization of V star, and consider the universal quotient here. From this, we get a sequence, H0I, OP minus 1, H0, omega OP to the cokernel, and then you take the cokernel. The cokernel is a bundle, and OPE1 yields a morphism, PE to P H0 omega, and the image is a scroll. And the image is a scroll containing C prime by construction. Okay. Now, I'm just talk about other notions of gonality. Note that we have used a notion of gonality, but we could have used other ones. And I'm going to just talk about how they interact with ours. So the gonality of C is the smallest D such that, I mean, the first, we could have adopted something like, there is a degree D morphism C to P1. What if we keep this notion? Look at what's going to happen. Rephrased, we're going to see that the gonality is rephrased as there exists an invertible F on C with degree of FD and H0 of F at least 2. This is the we rephrase this thing, but what if we have adopted this? It can be too large. For instance, I don't know if you still remember that I define what is a nearly normal curve. Then for those curves, we would have gonality G, and G is too high. It's too large. I mean, it's greater than G divided by 2 plus 1, which is the expected bound. We're going to see this for curves. Another one, which I saw in this paper, well, I didn't mention the paper, but okay. Hotchkiss-Eulery. They say, well, I like this paper, but the definition is too different from ours. There exists a degree D morphism C bar to P1. So it's too different because any rational curve would have gonality 1. Then there's this paper, whoops, well, what I'm doing? By Juliana and Fred, which I like a lot, this paper. I didn't mention the paper, sorry. But it's in Fred's PhD thesis. C is a limit of smooth curves all carrying a GD1. It's similar. We'll see the connection, and that's it. So let's discuss now an upper bound for gonality. The conjecture is that the gonality is at most G divided by 2 plus 1. For smooth curves, this comes from a very well-known result when consider the Brunner variety, and it is non-empty if the Brunner number is greater or equal to 0. And there are many people who addressed. Kleiman in 1857 addressed the case R equals 1. Brunner for sure. In 1874 addressed the general case. Mois, 1960, proved the result for R equals 1. AD1 is non-empty if ρ is greater or equal to 0. Martins, in 1967, the components of the omega, the WDR, have dimension at least ρ. Kleiman, Laxov, and Kempf, 1972, proved the result. Photon Lasersfeld, 1981, proved the result and got something else, that this variety is connected if ρ is greater than 0. So for singular curves, before addressing this thing, I'll just mention some evidence. First is that this bound holds for smooth bow curves. For instance, if you take a family, then consider this set GD as in S, such that gonality is at most D, then it's closed by a per semi-continuity applied to the universal sheaf on X times, times the compactified Jacobian, so maximal gonality yields an open set. And also, this makes a comparison with Freddy and Juliana notion of gonality also. And then in a paper with Contiero Feital, we noted that this bound also holds for monomial unicuspidal rational curves by means of it's pretty simple, but I think it's sort of interesting, this computation. Note, if you take this sheaf, suppose take the multiplicity of a point. If you take this sheaf generated by 1 and Tm, the degree is n. If you take, the section T, which defines the rational curve, the parameter, the parameter, sorry, at the singular point, then if you compute this degree, you're going to have something that it's smaller than G plus 3 minus M. So as these increase, this decreases, and maximal possible gonality will happen when M is G plus 3 minus M, and this yields exactly G plus 3 divided by 2. This is sort of interesting. Also, in our recent PhD thesis, a student of mine noted this for, well, this is not a result. The bounds holds for Gorenstein unicuspidal rational curves. I would say that it's far from being a result. But he was trying to find the GD1, then there is a computation there. And there was an interesting fact that the number of indeterminates was always greater than the number of equations, precisely when D exceeded G divided by 2 plus 1. So this number appears everywhere, even if you are dealing with a singularity and things like that. No, those curves, those rational curves here, they just have a singularity, and at the singularity, these things already appear. This is sort of interesting. Okay. So now let's finish and let's revisit photon lasers field proof. So he derived the result from a more general result, which is this one. Let sigma from E to F be a morphism of bundles of rank E and F on X. Set dk to be the degeneracy locus, X in X, such that the rank is at most K. And if E star tensor by F is ample, then dk is non-empty if dimension is greater than E minus K, F minus K. So how you derive from this result what we want? By this. You take X to be the Jacobian, I to be the universal sheaf on Cj, PQ to be projections, fix P0, take dt and consider this map. And you push forward this map to J, and you're going to have the sheaves E and F. And from this map, well, if you push forward this map, you're going to have that the Brill-Noether variety is going to be isomorphic to this degeneracy locus whenever T is M minus D and K equals M minus G minus R. So the problem now is to show that take the push forward of this, and consider this tensor product. Is it ample? And so don't have time. But the problem reduces to ampleness of Cm minus 1 plus P0 in Cm, where Cm is the symmetric product. And so in our case, some things can be adjusted, like one could replace J by the closure of invertible sheaves in the compactified Jacobian and consider this map instead. And then you're going to have the same thing, that omega dr is going to be the degeneracy locus of P star phi. I mean, I'm just putting the things which change. And so at the end, the problem reduces to ampleness of Q M minus 1 plus P0 in QM, which is now not a symmetric product, but it's a quote scheme. And then Eduardo came up with this construction. You take any singular point, take the D, the dimension of the tangent space, and consider P, TP. It is a PD minus 1 in key D, which doesn't meet key D minus 1 plus P0, sorry. So it is not ample. So that's what I had to say. Let me get back to you.
Thank you very much, Renato.
Sorry, I'm not escaping from here. How am I escaping?
No, you can leave your screen, no problem.
Yeah, I'm trying, but I can't.
No, you can leave it there. You can leave it open.
I can leave it open.
Yeah, I can leave it open, no problem. So let's thank Renato for his wonderful talk. Are there any questions or comments?
So you mentioned that the problem reduces to ampleness, right?
Uh-huh.
But it's not ample,
It's not ample.
right? So is there a new problem?
Well, I think that Steve can also talk about that, but feel free, Steve. Eduardo, yes, I think we have to choose another way, seems to me.
Yeah. I'm here. Yeah. So I don't know if you can hear me, but yeah. Can you hear me? No.
There's a lot of background noise, but we can hear you.
Okay, great. Well, I don't know why there's background noise, but anyway, the point is that if we had ampleness, then we could use the Fulton-Lazarsfeld proof to conclude what we want, the existence of special divisors. However, there are other proofs of the existence, the one given by myself and Dan Laxov and independently by George Kemp. And that proof involves intersection theory. You just compute the degeneracy locus that Renato mentioned. It's given by a certain polynomial in return classes. They turn out to be computable because of the Poincare formulas. So if we could prove the Poincare formulas for singular curves, we would be able to conclude the existence, even though the sheaf isn't ample. So I hope that mathematics proof might give us some ideas, but so far we haven't seen how to make it work. Is that clear enough, or should I say some more? So the degeneracy locus is just given by Porteus's formula, so we just have to compute the true classes of the bundles, the source and the target. But that's easy. They are the loci, the basic ones. So you can write down formally a determinant in powers of the canonical divisor. And the question becomes whether that number is non-zero. So we hope it is. We don't just see why yet. Okay, does that help?
Okay.
Yeah, well, yeah, Eduardo, I think that, well, photon laser field is over, I think.
What's that?
Yeah, I mean, photon lasers field is over. I mean, we have to choose another way.
Thanks, Eduardo and Steve. This is quite a dramatic statement, Renato. It's over.
No, I mean, no. It's been a suffering. I mean,
Okay.
this thing is.
No, if
But-
you were suffering, imagine the other guys that are over, right?
The other guys?
The other guys that are over, Laserfeld and Photon. Any more questions or comments for Renato? Okay, so I'd like to thank everyone for showing up, for attending this last edition of the BRAG this year. The 2000 and 2001 seasons were great. Let's see how we're going to keep it up next year. That's all for today. Let's thank Renato again for his wonderful presentation.